Good evening, students. We have already done wave functions and we have seen some beautiful graphs obtained from those mathematical expressions. Especially remember one thing, psi versus r graphs, psi square versus r graphs, radial probability versus r graphs. They will give a kind of distribution of the electron density around the nucleus. As we have already discussed earlier, we have seen the wave functions. For 1s orbital, if you take psi, just psi versus r, it was looking like this, an exponential decreasing function. And for psi square versus r, just take the function and take the variation of psi square with r, you will get something like this. But what about radial probability? As I told you, radial probability is the probability of finding an electron on the layer you have selected from a particular distance from the nucleus. So the radial probability curve of 1s, that 4 pi r square psi square dr versus r is like this. The last one gives an interesting feature, how the electron density is distributed around the nucleus at different distances. At one particular distance you can find the layer containing too much of electron density and it gradually decreases. This is for 1s. And for 2s, how does it look? For 2s, psi versus r is like this. See, there is a node at one particular distance, the psi started becoming negative. And if you take psi square versus r for 2s, psi square versus r, this is going to give you a positive value from there onwards. This negative part will go up because psi square cannot be negative. And the radial probability curve, we call it r square, you can say, radial probability otherwise, radial probability versus r for 2s is like this. As we already discussed this, there will be a radial node, there is a radial node, there is a radial node for 2s. For any particular orbital, the number of radial nodes is given by n minus l minus 1. Suppose you just take once all the list of quantum mechanical states available. N is 1, n is 2, this is all for hydrogen atom, n is 3, n is 4 like. And you have got 1s wave function and you have got 2s and 2px, 2py, 2pz. There are 3 orientations with same energy for p orbital. So there can be 3 acceptable wave functions. Similarly here what do you have? 3s, likewise 3p, there are totally 3 orientations, there will be 3d with 5 orientations. We have already done this. What I would like to tell here is, these are all what? Wave functions, and they are all quantum mechanical energy states. They will have their own shape. We call them orbitals, and the shapes of these orbitals we will just focus today for some time. The shapes of s orbital, p orbitals, d orbitals and f orbital. I just remind you the definition of orbital once again. The space around the nucleus, the region around the nucleus where the probability of finding an electron is maximum. So at least 95% probability should be there in one particular region to call it as an orbital. Orbital, it spends more time over there. You are walking somewhere, you come across hills, valleys and some flat regions, and in hill region you spend more time, in a valley region you spend more time. So the probability of locating you is more on a hill and valley. Where the height is more, there the electron spends more time. The reason is different. It has got its own convenience. So there are different such states around the nucleus. And what could be the shapes? And those shapes are obtained from the collected data of these radial probability curves and certain other polar based, means angle based mathematical expressions, everything is far beyond your scope of learning right now. So take me granted, what are the shapes of the orbitals, 1s orbital, 2s orbital, 2px, the shapes we should learn. We will focus for some time and try to understand what could be there, what could be some physical meaning we can derive out of it. Still some more language we will learn in this particular class. So what I would like to highlight here, as I said, 1s has no node, so 1s will be like this. 2s has one radial node. S is a spherical shaped orbital. 2s has some electron density around the nucleus with one node and again next density. See, there is a radial node. This is 2s. And 3s is what? There will be a small density, again some other density, with one radial node, one more radial node, again some more density. See, there is one radial node, one more radial node. There are two radial nodes. Node means where there is no density. What did you observe? When you move from 1s to 2s to 3s, all are spherical, all are spherical. And what are their L values? L is 0, L is 0, L is 0. What are their M values? M is 0, M is 0, M is 0. But where do they differ? They differ in N. N is 1, N is 2, N is 3. As N increases, the energy increases. 3s orbital has greater energy than 2s than 1s. And orbital angular momentum is same for all, because orbital angular momentum is given by root L into L plus 1 into h by 2 pi. And this value will be one and the same for all the s orbitals, because there is no n. So this is how you should understand. For same type of orbitals, s orbital group, p orbital group, d orbital group, as you keep increasing the n value, the energy will increase. Across s and p energies we will see a bit later. But for one particular orbital, the angular momentum will not change, and orbital angular momentum. Only thing, energy will increase. And the first least energetic orbital does not contain any radial nodes. Like here, there is no radial node for this. There is one radial node, two radial nodes. And among p orbitals, what are they? 2p, 3p, 4p. So there is no 1p. So 2p will have no radial node. So what will be the radial probability curve of 2p? 2p will be like this. Radial probability versus R. What will be 3p? One radial node. And what could be the shape of a p orbital? We will see. P orbitals are dumbbell in shape. Their shape is dumbbell shape. It will be something like this. Actually, we should not draw like this. The best way of drawing is this. This is the best way. Both together is one orbital. And there will be nucleus, and that particular wave function shows electron density. Here 95%, total put together 95% of the time electron spends in this particular region. We call it p orbital. And as I told you, there will be three possible orientations of a p orbital. Don't think one p orbital will be rotating like this, nothing like that. This is defined, this is defined, this is defined. All the three states can exist in the atom, hydrogen atom. So this is one p orbital. Now we will have to provide some references like x, y, z, because these three p orbitals are mutually perpendicular. So we can designate them with certain labels. So let us see. And my dear students, this is, let me say this is a 2p orbital. and it can exist in how many directions? 3 different directions. So let me tell you something. So we'll draw a cube so that we can clearly understand the 3 p orbitals. See, px, py, pz. There will be 3 orientations with -1, 0, +1 magnetic quantum number values. So px is oriented towards this face and this face. What do you call this? Px. Py is oriented from the up to up and down, top face and bottom face. Py, and pz is oriented back and front. We'll go for which color? We'll go for violet or yellow, which is more visible, green. So see, this is pz. Can you see this green color? Should I change so that it will be a visual feast for you? Gold color, yeah. There are 3 varieties of p orbitals. They are mutually perpendicular. See, this is px. Px. We call it as py, and this is going to be pz. What is the angle between the 3 p orbitals? 90 degrees. One goes along x-axis, one goes. Don't think there will be axis in the atom. There will not be any axis. The 3 mutually perpendicular p orbitals are designated with reference axis. We take them, assume them to be present on x-axis, y-axis and z-axis. Here I would like to tell you one particular thing. Whatever is present on z-axis will receive magnetic quantum number 0. This is a conventional number. Magnetic quantum number for anything that lies on z-axis should be 0. We will see that later. Here I would like to tell you one beautiful thing. We have already seen radial node. What do you mean by radial node? Where psi square value becomes 0 based on where psi becomes 0 at one particular distance from the nucleus. Here there will be an angular node. Angular node means when in one particular theta value, the psi will become 0 for some cases. And the other day I showed you some wave equations. S orbitals wave equations do not contain thetas and phis. There is no angle part for S wave function, 1s, 2s, 3s. Those wave functions do not contain angular part. What does that mean? In that s orbital, in whatever direction you change the angle, psi square will not become 0. But in P, what will happen? If you change the angle, see, this is P. If you keep changing the angle, psi value keeps on changing, and one particular angle, psi totally becomes 0. So this is the plane. This is the plane. This is a plane on which px orbital is not defined. There will not be even a pinch of density of px orbital present on this particular plane. What is that particular plane? You can call it, it is made up of y-axis and z-axis. So you can call this plane as which plane? YZ plane, because that plane is made up of y-axis and z-axis. This is px orbital. So px orbital is cut with a plane on which there is no electron density. We call that plane as nodal plane, or it is called as angular node. So px orbital has one angular node. Px orbital has one nodal plane. So it is a plane which divides the orbital into 2 equal parts, on which psi square is 0. So how do you define a nodal plane? A nodal plane is a plane on which electron density is 0, and the plane should divide the orbital into two exactly equal parts. That is a nodal plane. Suppose you have got a p orbital like this. Why don't you take this as nodal plane? Why don't you take that as nodal plane? This is also dividing the orbital into two equal parts, but this is not nodal plane because electron density is not becoming 0 on that plane. So nodal plane means a plane which divides an orbital into two equal parts on which psi square value becomes 0. So how many nodal planes can you find for a p orbital, px? There is only one nodal plane. For each p orbital, there will be one nodal plane. For px, what is the nodal plane? YZ plane. Now you take py orbital, what will be the nodal plane? Py. This is py. What will be the nodal plane? This one. The one which is dividing orbital into two equal parts. This is the nodal plane. See, this is up, this is down. And what is this plane? This is going back and going like this. This is py orbital. And what is this plane? XZ plane. This is Z, this is X. XZ plane. So XZ plane is the nodal plane of py orbital. So pz orbital will have which plane? The xy plane. Xy plane is dividing pz orbital into two equal parts on which psi square value is 0. So what is the conclusion? S orbitals, let it be 1s or 2s or 3s, there will not be nodal planes. There will not be angular nodes. For p orbital, for each p orbital, there will be one angular node or one nodal plane. Suppose you have got 3px. How many total nodes are there? You can say for 2p there is no radial node. For 3p there is one radial node. And whatever may be the p, there will be one angular node. There will be one nodal plane. Every p orbital contains one nodal plane. So this 3p has one radial node, one angular node. Like that we tell. Now my dear students, let us go to d orbitals. D orbitals. What is the degeneracy of d orbitals? How many orientations are there for a d orbital? -2 to +2. -2, -1, 0, +1, +2. -2 to +2. There will be 5 orientations of a d orbital. They are designated as dxy, dyz, dzx, dx square y square, dz square. This is a conventionally designated names. You should never change them. This is globally acceptable names. What do you mean by dxy? Actually, d orbital contains more number of nodal planes. That is why energy is more. So each d orbital contains two radial nodes. Sorry, two nodal planes. There will be a double dumbbell shape. A d orbital looks something like this. All the 4 balloons like lobes put together makes one orbital. All the lobes together, one orbital. Don't think this is one orbital, this is one, like that. Entire space, the space where d electrons can be found with highest probability. So that is why it's called a d orbital. Now all the d orbitals have got their relative orientations in the space. So if you take to reference of the Cartesian axis x, y, z, will designate these d orbitals like this. Let us see. This is x axis, this is y axis, and if the lobes are like this, see how are the lobes spread? They are spread in between axes. So this is called dxy. If the lobes spread between y and z, back and front, so I am only changing the labels, y and z, this is called, dyz. If the lobes spread between x and y, y and z, z and x, like this. So these three are, this is what, d zx. Now coming to dx square y square is like this. The lobes are spread on, x and y. Lobes are spread on x and y. So we call it dx square y square. dz square has a peculiar shape. On the z axis you have two lobes, and xy plane there is a torus. We call it a collar. Torus, collar like, a dish like, yes, one disc like. See the tenicoid they play, that lies on the xy plane, and the lobes will spread along the z axis. So 5 d orbitals, and as I mentioned earlier, this must get m value 0. Its name is dz square, and the remaining -2, -1, +1, +2 m values, and this m value is 0 because totally z, oriented on z. Now how many nodal planes are there for each d orbital? So how many nodal planes are you seeing here? This is one plane, this is another plane. So each d orbital has 2 nodal planes. Here 2 nodal planes, this one, this one. This d orbital, see there are 2 nodal planes. This d orbital, this is one nodal plane, this is another nodal plane. But this d orbital has no nodal plane. Why? Because if you see this, you can cut it into 2 parts, but on that plane this tenicoid kind of, collar kind of density is spread on the xy plane. Therefore you can say dz square has no angular node. There is some nodal region, 0 electron density region is there, but it is not a nodal plane. So s orbitals do not contain nodal planes, dz square does not contain any nodal plane, and each p orbital contains 1 nodal plane, each d orbital contains 2 nodal planes, and f will contain still more. We do not go into complicated shapes of f orbitals. We will still understand something about these orbitals. Let's see, that is s orbital. The spread, the density is spread exactly in spherical symmetry. So even if you change the angle also, nothing will change. I don't have the wave functions now. If you can just see the previous videos, I show s orbitals wave functions do not contain theta, sin theta, cos theta. You won't find in the wave function solutions for s orbitals. Like that only you can recognize s orbitals. If at all they give a big mathematical expression as a wave function, and there is no theta there, immediately you can recognize that is an s orbital. You know? P orbitals. See, there is a node. More the nodes, higher the energy. So what do you mean by this plus and minus? Don't think it is any charge or anything. It is only wave function sign, positive sign and negative sign. Don't think it is a positive charge or negative. After all, it is a region where electron spends more time. So if it is divided like this, you will find a node. There is a nodal plane, angular node. So Px. Px means the lobes are spread along x-axis. Py, the lobes are spread along y-axis, electron density. Lobes are spread along z-axis. Now see the shapes of d orbitals. How beautiful they are. If you see x and y, see this is x-axis, this is y-axis. See how the lobes are spread? They are spread in between the axis, between x and y. So it is called dxy orbital. So here the lobes are spread between xy planes. So we call them dxy, xz. And here the lobes are spread in between y and z axis. So we call them dyz. Here the lobes are spread on the axis, along the axis. So we call them dx square y square. And here the torus is clearly appearing. See, there is a beautiful torus. So that is dz square. Each orbital has two nodal planes. dxy. What are the nodal planes for dxy? xz and yz planes. For dxz, xy and zy planes. yz, xy and xz planes. For this you can't find Cartesian planes. And for this there is no nodal plane because the torus is there. So these are d orbital shapes. Now let us go to the most important aspect of this chapter. See, finally what is our objective? If you just think of 18 days before we started the chapter, I said what could be the conclusion of the chapter? I said we can't conclude. Yeah, we did not conclude anything. These are orbitals. Orbitals means probable regions. They are not exact places where electron spends its time. These are the probable places where probability, uncertainty. So final conclusion of the chapter is uncertainty. So these are probable places where electron can stay. So let me draw a few wave mechanical energy states of electron in a single diagram. See, this is a nucleus. 1s is a spherical orbital, very small orbital. This is 1s, spherical. 2s, a bit larger, but spherical. This is 2s. What about other orbitals present in second principal state? 2p, 2px, 2py, 2pz, 2px. This is 2px. 2py. This is 2px. 2py on the y-axis. 2pz on the z-axis. Then comes 3s, which is larger than 2s. It's 3s. And you have 3px, which will be in x direction only, but larger than 2px. With a node. 3px, 3py larger than 2py. Two py, 2pz, 3pz, sorry. We have got in third principal state D also, dxy, dyz, dzx. dxy 4 lobes, dyz 4 lobes, dzx 4 lobes, dx square y square along x and y, dz square with a torus. Almost some picture you can take like this. Every well defined quantum mechanical states are present around the nucleus. All energies are quantized energies. Energy gaps will be rhythmic, there will be quantization with some discipline. So, how to get the relative energies of these orbitals? Actually, n plus L gives the relative energy of orbital. Don't think it's an absolute energy, it's only relative energy. What is the energy of 1s? Relative energy. 1s. What is n value? 1. For s, we have already learnt L value is 0. So 1. What is the relative energy of 2p? 2 plus, for p L value is 1. 3. What is the relative energy of 3d? 3 plus d is 2. 5. So it's like that we'll have to work out. But then those numbers will only give the relative energy to compare the energy states. That is not absolute energy. How can absolute energy be simple numbers? It should be some kilojoules like that per mole. Each energy state will be given like that, some values. Don't bother about it. So to compare the energy states, we can use always n plus L rule. There will be some troubles. So 3D, how much you got? 5. 4p, 4 plus 1, 5. This is also 5, this is also 5. For 3D, 4p, we have got same n plus L value. Then which is more energetic? If n plus L value happens to be the same, you should give priority for n. Which has got higher n value? This. So 4p will have more energy than 3D. So if n plus L value happens to be the same, if you want to compare the orbital's energy, the one with greater n value you should prefer to have more energy. My dear students, and this will help you build a sequence of quantum mechanical energy states of electron in hydrogen atom around the nucleus. Here I want to highlight a very big word to you. Let me tell you. You have 1s, n is 1. You have 2s. What else do you have? P, there are 3 p orientations. So you have 2px, 2py, 2pz. Let me warn you, let me advise you, let me highlight a point. All the 4 orbitals, each box is one orbital. Remember, there are 3 orientations, means 3 different orbitals for p level, p energy. 2s, 2px, 2py, 2pz, all the 4 orbitals possess the same energy. You may ask me, just now you told n plus L rule, why are you telling like this? In single electron species like hydrogen, helium plus, and all those things, these orbitals do not depend on L value or M value or S value. The energy of an orbital simply depends on only N value, because in hydrogen like species, single electron, single nucleus, there are no other influences. So the energy of the other quantum mechanical states are not affected by their orientation, their angular momentum, like. They all simply depends on their principal energy state. That is the reason we are successfully able to explain hydrogen spectrum of single electron species simply based on n values using Rydberg equation. See, this equation is totally correct as per hydrogen spectrum is concerned. We are able to explain how many spectral lines are formed, what is the energy of a spectral line for a given transition, everything accurately you are able to calculate. Means what? In hydrogen like species, simply energy of a state depends only on the principal energy state. It does not depend on it. Do you have L or M or N, S there in the Rydberg equation? You have got only N. What does that mean? Only one electron is there in any species, hydrogen, helium plus, lithium plus 2, beryllium plus 3, like. In a single electron system, the energy of the orbitals depend only on N value. What is the N value for this 2? N value for this 2, N value 2, N value 2. As long as N value is same, their energy will be same. So energy of 2s is same as 2px is same as 2py is same as 2pz. How many quantum mechanical energy states are there with principal quantum number 2? There are 4 energy states. So that is called the degeneracy. Degeneracy means 4. That 4 is called the degeneracy. Degeneracy means number of quantum mechanical states with equal energy. What about the next energy state? How many? What is the degeneracy of this? Means how many wave mechanical energy states are present with n value 3? There is 3s, there are 3 p orbitals, there are 5 d orbitals, total 9 orbitals are there. So 9 quantum mechanical states are available with same energy. But this has more energy than this because principal quantum number changes. As the principal quantum number increases, energy will increase. Once the principal quantum number is same, energy of all the orbitals is same if the species is a single electron species. If it is not a single electron species, their energy will not be same. So, who has the least energy? 1s. Next best energy, 2s. So, next least. Then comes what? Its energy is less than them because n plus L value is more for them. And what is the n plus L of this? 2 plus 1, 3, 2 plus 1, 3, 2 plus 1, 3. All of them have same n plus L value. So, 2px, 2py, 2pz have same energy. So, degeneracy is 3. 3 orbitals with same energy. Then comes what? 3s. Because principal quantum number is more. Then 3p. In 3p again 3px is equal to 3py, 3pz. All the 3 have same energy. So this is how you have to go for the order of energy in polyelectronic species. In a single electron species, the just depend on n value, how many quantum mechanical states are there with a given n value. Now my dear students, let us build up a beautiful thing. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. This is all the energy increasing direction, 6s, 6p, 6d, 6f like. So electrons first prefer to enter the least energy orbital, 1s. Suppose you go to cricket ground, you prefer the first row to watch the match. Suppose you are going to a movie theater, you prefer to sit in the last place. So like that, electron prefers to occupy the least energetic orbital first. That is called Aufbau's principle. So after this is filled, electrons will go to 2s, then 2p, 3s. This is the order in which electrons will enter into different orbitals. My dear students, always remember one orbital can accommodate only 2 electrons. Let it be s orbital, let it be p orbital, let it be d orbital, let it be f orbital. Never have a bad habit of saying how many electrons can be filled in a d orbital. Most of the 90% students are now telling 10 electrons. They are counting all the orientations together. That is not a correct method. An orbital can take only 2 electrons, one with positive spin, one with negative spin, with half spin, positive half spin state, negative half spin state. So orbital can take 2 electrons, s orbital can take 2 electrons. When it comes to 2p, there are 3 orientations. Each orientation is 1 orbital. So each orbital will take 2 electrons. So entire 2p state can take 6 electrons. 3d state can take 10 electrons together, because all the d orbitals have same energy, like that. So how to fill them? Aufbau principle. In ground state of the atoms, the orbitals are filled in the order of their increasing energies. Among the available orbitals, the lowest energy orbital is first filled with electrons. The increasing order 1s, 2s, 2p, 3s, 3p, 4s, 3d. Did you observe here? 4s has come first, 3d came later. Why? 4s has 4 plus 0 energy, 3d 3 plus 2 energy. 3d orbital has greater energy than 4s orbital. So 4s should be filled first, then go for 3d, then go for 4p. I showed you an order in the previous slide. See 4s, 4 plus 0. After that 3d, 3 plus 2. So like that. See, this is the order, Euler diagram. Just now I drew, the same thing. Pauli's exclusion principle. No 2 electrons in an atom can have the same set of quantum numbers. See, once one electron is there in an atom, it is designated with a unique wave function. In that wave function is an orbital. Electron will either rotate with positive spin or with negative spin. Means what? Clockwise or anti-clockwise spin allowed. There is no otherwise. Clockwise and anti-clockwise. How can there be otherwise? As half spin or negative half. So electron can have only one kind of spin state, and remaining NLM can never be duplicated. So every electron is designated with a unique set of quantum numbers. You cannot have 2 different electrons with the same quantum numbers. How can your house and the neighbor's house have same phone number? A phone number is unique for a given house, a given person otherwise. Phone number is unique number. All others cannot have the same number. Right? So like that, electron designation is done with 4 unique set of quantum numbers. 2pz. So what are the quantum numbers of this electron? This electron, n value 1, n value 2. So n is 2. What is L value? Because it is in p orbital, L value is 1. What is m value? 0, because z orbital. S is minus half, downward electron. Now no other electron will have this set, no? How can other electron have the same set of quantum numbers? No chance. So Pauli's principle says every electron has an exclusive set of quantum numbers. The electron's designation is done with a unique set of quantum numbers. No other electron can imitate the quantum numbers, duplicate the quantum numbers. Sorry. Hund's rule. Suppose, as I told you, in polyelectronic system, polyelectronic atoms, more than one electron, you will have different orientations of an orbital. Let's see this. N is 1, N is 2. Here you have S, but P you have 3 orientations, 2px, 2py, 2pz. I want to fill 2 electrons in these orbitals, 2 electrons. Now, 1 electron is already filled. So, 1 more electron is there. Now, I have a dilemma. Where to fill it? Should I fill it in the next equal energy orbital, or should I go for pairing of electrons? Always see that the magnetic moment is maximum. Means there should be as many parallel spin electrons as possible within a given set of degenerate orbitals. Degenerate orbitals means orbitals with same energy. 2px, 2py, 2pz have same energy. Once the energy is same, you want to fill electrons, see that, fill multiple electrons, see that the spin is maximum, because all electrons should spin in the same direction. Suppose you want to keep 1 more electron with the same spin here, that is not allowed according to Pauli's exclusion principle. So you have to go for next only. Don't pair up like this. When there are only 2 electrons, don't do this. This is wrong. This is correct. Whenever a set of degenerate orbitals are available, if more electrons are there, electrons should get paired up only after each orbital is filled with 1 electron. Pairing up of electrons in degenerate orbitals take place after filling each with 1 electron with parallel spin. Don't even change the spin in the equal energy orbitals. That violates Hund's rule. It deals with filling up of degenerate orbitals with electrons of equal energy orbitals. So don't pair up electrons in a set of degenerate orbitals until all the degenerate orbitals are half filled. I have P4 configuration. P4 means there are 3 p orbitals. 1, 2, 3. You have to fill like this. That 4th electron, it has to pair up. Don't do like this. This is also wrong. What is this? Is it a violation of Hund's rule or is it a violation of Pauli's principle? See, if you give this kind of configuration, both will have same quantum numbers, same principal quantum number, same azimuthal quantum number, same magnetic quantum number, same spin quantum number, which is not valid according to Pauli's principle. So, you have to go for a reversal of the spin. This is correct. Don't do like this. This is also wrong. This is violation of Hund's rule, because as per Hund's rule, don't pair up until all the orbitals are half filled. And you should also see that maximum spin is available. So maximum parallel spin should be available. Sometimes we violate certain things. I'll come back to this point again. In the meantime, we'll just go through some configurations. Suppose I have got hydrogen atom. It has got only one electron. Where should I keep that electron? In the ground state. What is the best possible state? 1s1. Because it should be kept in the least energetic state. Now helium, atomic number 2. So fill both electrons in S, 1s2. In lithium, what shall we do? Lithium has 3 electrons. So 1s is already filled with 2 electrons. Then what is the next best orbital? 2s. So go to 2s. And because of this configuration, what can you tell? Lithium has got one unpaired electron. This is 2s. Don't write like this. To satisfy half bow, don't do like this. Whom are you violating? You are violating Pauli's principle. You are giving same quantum numbers to these 2 electrons, which is not valid. No 2 electrons can have the same set of quantum numbers. They are not allowed. Each electron must have an exclusive set of quantum number. No other can have that quantum number set. So this is a violation of Pauli's principle. So don't do like this. You have to go by this. Coming to oxygen configuration, you have got 8 electrons. First fill 1s with 2 electrons, then fill 2s with 2 electrons, then go for 2p. 2p 4 electrons can go in the entire all the orientations. So in this 2p4, what is the configuration? 1, 2, 3, 4. So 2 unpaired electrons. There are 2 unpaired electrons in oxygen. Putting all the 4 in 2 orbitals is a wrong practice. So what will be the configuration of scandium? Scandium atomic number is 21. Fill 1s, then fill 2s with 2 electrons, 2p x, 2p y, 2p z with 6 electrons, 2 each, 3s, 3p again 6 electrons. So totally how many electrons are over? 18 electrons are over. This is 21. After 3p, electrons enter into 4s, 4s2. Then electron goes to 3d, 3d1. So what is the configuration? At the last configuration is 3d1. Highest energy electron is 3d1 electron. Now let us go to chromium, whose atomic number is 24. One s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Actually, this I have written according to this order. But in real chromium atom, the configuration is rearranged. It will not be like this. This 4s2 is like this. It's a completely filled orbital. d4, you have got in the 5 orbitals, 4 electrons are distributed. 5 orbitals, dxy, dyz, dzx, dx square y square, dz square, like this. Neatly distributed orbitals in the space. but only 4 are filled with electrons, 1 is not filled with electron, the spherical symmetry will be lost. There will be imbalance in the electron density distribution in the orbital. And so what may happen, the one electron present in 4s instead of being here, it will join here, so that all the d orbitals are equally filled with 1 1 1 electron. So what may happen, this will achieve spherical symmetry. So whenever you have half filled configuration, now the configuration becomes what? 4s1 3d5. D can maximum accommodate 10 electrons. Now there are 5 electrons accommodated. So either 10 or 5 for D is a good configuration. Generally orbitals with half filled configuration and completely filled configuration are generally more stable. So there can be some rearrangements like this can occur in anomalous configurations, you can see in some atoms. Even in copper it happens. Copper 29, 4s2 3d9 is the last configuration. This also changes to 4s1 3d10. So d10 is better than d9. Actually there is one more explanation for this, electron exchange energy explanation. That can be done, we will see that. Symmetric distribution of electrons. Completely filled, half filled subshells have slightly extra density, extra stability. See 4s1 3d4 d5 sorry. So these electrons can exchange among themselves rapidly. That rapid exchange phenomenon will give extra stability. Who can exchange? Orbitals of close energy, if they have same parallel spin electrons, they can quickly undergo some exchanges. Because of such exchange, the system will be stabilized. How many electrons can show some exchange now? 6 electrons are in exchange phenomenon. If you keep it 4s2 3d4, 1 2 3 4 parallel spin electrons, 1 2 3 4 5. Here 6 electrons are exchanging, here only 5 electrons are exchanging. So this is more stable configuration. So like that there will be some anomalous configurations, we will see, we will learn it. So my dear students, we have thoroughly learnt the beauty of the work, almost 100 years work of many scientists whom I showed you in the beginning. And finally we are now enjoying electron configuration for every atom. Now we will be able to understand why sodium behaves in a different way than magnesium, than aluminum, than silicon, than phosphorus, than sulfur, than chlorine, than neon, argon, why gold is like that, why mercury is like that, why iron is hard. All the things we can explain on the basis of electron configuration. Now we will switch over to periodic table and we will try to enjoy the placement of elements in the periodic table with reference to their electron configurations and properties in our next session. Just keep going through all previous lectures once again. Get used to such language. Have a good day. Enjoy. We will meet in the next session.